Hi, my name is Amir from Tohoku University, and I'm presenting PSM, a predictive safety model for body motion based on the spring damper pendulum. Robots are getting into the human's daily life day by day, and the workspace environment is very important. At first, the robots were given a fixed safeguard place where when human enters that environment, robots would stop. Next, we had more interactive actions, like where the human gave a guidance to the robot, and the robot tries to follow the trajectories continuously. Recently, we have more advanced strategies where we have applied the human intention and created dynamic environments and workspaces where the robots try to assist the person based on his location in the environment. Also, there have been studies on force limiting and creating torque-based reaction based on the human inputs to create a more ergonomic interaction between the human and robot, as well as adding different sensory inputs like LiDARs to make the mobile robots to go autonomously between the humans. However, human safety and real-time risk assessment is very important when the robots and humans are interacting with each other, especially in daycare and assisting. For example, in our case, we have seen that the humans state mostly ignored and considered as a black box when we want them to interact with a walker robot or a Roomba robot, or to drink a drink or sit on a wheelchair robot. And this clearly showed that human state and real-time risk assessment is mostly ignored. Based on this motivation, we propose a dynamic and continuous quantification of safety in the human motion upper bodies. Safety in this study is divided to different levels, from the normal to unsafe and unstable motion of the human orientation. And this could give us more information from the stiffness and damping properties of the human motion to the coexisting robots in the environment. Based on our motivation, we have proposed a 3 degrees of freedom pendulum model with a spring damper compensation for a human upper body, which is connected to the IMU information on the human chest. And we have the following general dynamical model. And the objectives are obtaining elastic tracking based on the reduced dimension prediction safety dataset, where we have the estimated stiffness and damping values, which are obtained by the information from the IMU, and also the estimating the exerted torque by the human motion. The estimation happens by the prediction model and the safety dataset that I will explain. To understand the PSM model better, we have the following block diagram, where at first the human motion information from the wireless IMU sensor on the human chest is sent to the probability dataset. This dataset is a prediction form that has the reduced dimension probability, with one axis as the norm of the angular velocity of the human body, and the other is the angle of the body with respect to the gravity. And it is followed by the function of the probability distribution. Next, the information is fed to 1 degree of freedom pendulum model, which help us to calculate the safe prediction probability and the previous steps probability. And finally, we fed the information to our 3 degrees of freedom elastic pendulum model to find the error in the real time for having the continuous tracking of the safety. To have more details about this prediction in the projected dimension, the arbitrary pendulum model first is used to find the predicted probability in the previous step, which has the following elements that can be found by the probability data set with regard to the norm of the angular velocity and the angle with respect to the gravity. Also, the predicted probability for the safe motion is obtained by definition of the highest probability with the expanded horizon in the probability distribution. In this study, we have considered a real scenario where the patient gets up from the bed and prepares himself by tying the shoes, and then stands up and moves toward the toilet. And our data set is prepared with doing experiments using unbiased Gaussian distribution. And we ask the different participants to do discrete motions for each transition from low to the high velocities. And following is our obtained data set probability distribution. Also, in our experiment, you can see the gray pendulum as the human upper body motion. The safety pendulum model is also as the orange one, which shows the difference. And our constraints on angular velocity and angular orientation are distributed with different colors from high to the low, as the safest to the unsafe and unstable motion in the red color. And we have done this experiment in an explained scenario, where at a first video, you can see the normal motion of the participant. And we have observed the angular velocity, angular orientation constraints with the green and sometimes the yellow color, which demonstrates that humans follow a safe motion. And mostly our PSM model, as the orange one, follows the same motion as the human upper body. However, in the unsafe and unstable motion, in the second video, we have mostly red and sometimes yellow colors, which presenting this person is not following the normal motions, and the sudden changes creates large deviations between our PSM model from the human upper body motion. In the demonstrated experiment, we have used the following values for the PSM parameters. Also, you can see the results for the angular orientation and velocity for the human motion and also safety model, where we can see the safety model has large deviations when humans show unsafe and unstable orientations. Also, we can see it in both angular orientation and angular velocity. In more details, the RMS error is applied in time and frequency domain, where we observe that during the normal motion of the human, the amplitude of the error is very small. However, unsafe motions can be easily detected in different frequencies by the PSM model, which you can see in the red color. And also, we did the success percentage evaluation for different participants, which shows that our PSM model, in average, shows over 90% success rate in different velocities from low to the high. As conclusion, the PSM model recognizes and evaluates the safety of the human motion at different levels using a single IMU, and the model quantifies the safety in real time based on angular orientation and velocity for human upper body motion. We presented the capabilities of the PSM in real-world scenario. And as a future work, we will apply this model to cooperative robots to work with wheelchairs and walkers in different scenarios. Please see the preprint for more information. Thank you so much for the listening.